Ladies and gentlemen, gallium nitride is an amazing new technology to achieve ultimate efficiency and power density in power converters. While GaN has rapidly entered the market in the consumer space, as for example in compact chargers for mobile devices, there is still concern whether GaN is already mature enough to meet the stringent quality and robustness demands for industrial applications, like server and telecom power supplies. In the following, I will show you how and that Infineon's CoolGaN is meeting those industrial requirements. In order to qualify a product, you need to know the requirements from the application. There are 4 important dimensions. The application profile lists the relevant operating conditions the device will see. The quality requirement profile defines the environmental conditions, required lifetime and acceptable failure rates. However, the most important inputs come from the reliability investigations during the development, identifying the relevant failure modes for this new material system and deriving the proper degradation models for each of those failure modes in order to determine the lifetime in the given application. The usual minimum requirement for product qualification is the JEDEC qualification, mostly consisting of static tests for typically 1000 hours. As an example, you can see here the fully passed qualification of our 600 volt CoolGaN GIT. But if you look now for the sample size, about 240 parts, and match it to the industry requirements of 1 fit failure rate over time, you see that by this qualification the detectable fit rate is by far too high to prove that the 1 fit is met. So here we need to extend the classic product qualification by lifetime modeling to properly determine the fit rate. As an example how that looks is if we look at the static DC bias, so drain bias, we run highly accelerated tests with test to fail. We track the time to fail for different conditions, different voltages, different temperatures. By the proper lifetime modeling, we can extrapolate out to the use condition. And in this so-called Weibull plot, now you can extrapolate down this intrinsic lifetime to the required 15 years and 100 ppm failure rate. And we see that we indeed achieve this target by even more than a factor of 3. Just for example, the previous JEDEC conditions of 3 × 77 parts for 1000 hours, you can see that they are far apart from this intrinsic lifetime that is needed. Now, this is the intrinsic part of the device, showing this once again, that the low number of parts only allows you to determine the failure rates of around 1000 fit. However, we want to really get a good feeling for the early life failure rate. For that purpose, we have conducted a large-scale burn-in study with more than 100,000 parts for different voltages and different temperatures, with a cumulative device hours at about 8 million hours for this burn-in study. And we had been able to extract now a separate lifetime model for this extrinsic branch. Only by that we come to the conclusion that the total overall failure rate in DC bias conditions is less than 1 fit. Now, the device is being used in applications where it's being switched. So that means the traditional testing, mostly dominated by static conditions like HDRB, gate bias, humidity testing, high temperature storage, does not address the most dominant failure modes in GaN that are connected to dynamic effects and switching robustness. Here, new design tests are necessary, and Infineon has sponsored new JEDEC documents to address this need, especially switching reliability and continuous switching evaluation. On top of that, we have developed a setup to qualify the switching robustness, where the test system allows to put a half bridge under switching conditions so that we qualify also both positions in the half bridge. And the system allows us the full monitoring of the device condition over the switching stress. And with this setup now we have again run the same like we have seen for the static DC biasing, here now for hard switching reliability. So we have run hard switching under highly accelerated conditions, so with DC link voltages far above the use conditions. Again, extracted our time to fails and modeled the degradation, so that we can see that we again also for continuous hard switching achieve the one fit intrinsically. On top of that, we have also tested the hard switching reliability with extended operation times of up to 3000 hours at elevated DC link voltage that is an equivalent to about the 12 years of operating at 400 volt use condition, where we see that we don't see any efficiency degradation nor hard fails. Again, hard switching, you can also have extrinsic defects that would cause early failure rates. And again, we have assessed this by running huge statistics under hard switching conditions, where we again went for highly accelerated conditions, 700 volt bus voltage, transient peak voltages of 770 volt versus the 400 volt typical conditions. And again, have conducted a large number of tests that in total, with the previous derived lifetime model, is an equivalent cumulative 1 billion hours of hard switching stress at 400 volt without fail. And that again demonstrates the one fit industrial requirement for the hard switching. Next point, how about the maximum allowed DC bias for the device? In power systems, typically we have to deal with transient voltages, and gallium nitride here comes with a specific property that it doesn't show avalanche capability, but the transient voltage capability is above the datasheet condition. You can rate your application whether it's fitting to those needs. We have put into the datasheet also a transient drain source voltage rating that gives you the allowed amount of time that you can spend above the 600 volt rating, which goes up to 750 volt. So this is now a transient spike rating, but there is another effect when it comes to power line surges, for example, caused by lightning strikes. The requirement here is that you do not only need a transient voltage capability, but you also need a device to survive the full hard switching at highly elevated DC bus voltages. And that is another point that we have proven and added to the datasheet, so that we have a switching surge voltage of 750 volt, which means that the transistor survives the hard switching at a highly elevated bus voltage of 700 volt for a number of minimum of 10 million pulses. Another point when it comes to robustness in a power system is that also the peak current capability is an important thing for high power applications. And as an example, during an AC line cycle dropout in a PFC stage, the bus voltage needs to recover after the line cycle dropout, and during that condition the transistor needs to switch highly elevated peak currents under hard switching conditions. This is something where you need to pay attention to the pulse current ratings in the datasheet. So for Infineon cool GaN, you see here we have for the 70 milliohm a 60 amp room temperature and 35 amp hot pulse current rating. If you compare a similar RDS-on device from a competitor that has the same 60 amp peak rating at room temperature, no hot rating given here. If you now put those two parts with equal peak current rating into a double pulse system and run a hard switching test up to the rated peak current, you can see here on the left side, this is the Infineon GIT cool GaN, where you see that at room temperature we can go for hard switching beyond the 60 amp peak rating while still maintaining low RDS-on values. And the other part that we have seen previously with this same 60 amp peak current rating, already at a little bit less than 40 amp, the transistor shows significant current collapse. So if we summarize, For the GAT cool GaN, we have put a pulse rating into the datasheet that you can trust in the following respect: that the 35 amp at 150 degree T-junction covers the 3 use cases. It's a single pulse SOA rating up to the full 600 volt at short pulse conditions. It's the same 35 amp valid for continuous hard switching over lifetime at 400 volt bus voltage in a repetitive SOA. And as shown before, it's also the same 35 amp valid for the dynamic saturation current on a hard switching. So coming to the end of my talk and summarizing, we have qualified our CoolGaN 600 volt device to conditions based on application specific stresses to target lifetime and quality requirements. The proof for fitness of use in industrial applications is based on lifetime models extracted for both intrinsic and extrinsic branches to cover also the infant and early mortality rate. Of course, our devices are qualified according to the new GaN JADEC conditions, where Infineon also contributed actively to the documents. And also our datasheet pulse ratings, both current and over voltage, are proven also for switching conditions. And in a nutshell, I want to say Infineon's CoolGaN achieves ultimate robustness and reliability. So thank you very much for your attention.